Chapter 3, Part 1, the very beginning, an introduction to acceleration. First of all, what is acceleration? The definition of acceleration is the rate of change in velocity. It's not enough to say that it's a change in velocity. Of course, if you accelerate, your velocity changes. But it's not how much your velocity changes, it's how fast your velocity changes. The units of acceleration are going to be meters per second squared. Now that second squared comes from it's a time rate of change in velocity. So it's how fast the velocity changes, which is meters per second, divided by time, which is another second. The equation for acceleration is a change in velocity divided by the time interval. Okay, so having time in the bottom makes it a rate, and it's the rate of change in velocity. Units, meters per second squared. It's a velocity unit divided by a time unit. So you could have meters per hour squared. A weird unit, but one that we see a lot, would be miles per hour per second. Oops, C-O-N-D. So if you changed your velocity, you're driving a car and you're going 40, and you increase your velocity to 60 in 20 seconds, you'd have a change in velocity of 20 miles per hour in 20 seconds, or 1 mile per hour per second. So it's a velocity unit divided by a time unit. Typically in our class, it will be meters per second squared. Squared because there are 2 second units. When we look at a graph of velocity versus time, now this is different. Last chapter we did position or distance time graphs, and now we're going to be looking at velocity time graphs. If I find the slope, and this graph has a slope of 5, a change of 1 in this direction and 5 in that direction would be a change of 5 over 1, or a slope of 5. The units will be meters per second divided by seconds. It's the change in y over change in x. And so for a velocity time graph, the slope is equal to the average acceleration. So slope of a velocity versus time graph equals average acceleration. Now acceleration is a vector quantity, and that means it has magnitude or size, and it also has direction. Acceleration can be positive or negative. If we look at this motion diagram, we have an object that's moving to the right. We can tell it's speeding up because the dots get farther and farther apart, and that means that in the same time interval they're traveling farther, so they're getting faster. If I compare two velocity vectors, remember acceleration is a change in velocity over time, and change in velocity is v final minus v initial, right? So if we look at that delta v, or that final velocity minus initial velocity, and remember, think vectors. If this is a final velocity and the initial velocity had been, like, they're comparing these two, and this would be vf, see, it's that size, and this one would be vi. We want to find the difference in them. A difference is subtraction. When we add two vectors, we would say this vector plus that vector would equal one big one that big. But if we subtract, then if we want to subtract, this is 1 and 2. If we want to subtract 2 from 1, well, here's 1. And we don't add 2 on to the end, we flip it around. It's just like adding negative numbers. So if I want to subtract 3 from 7, it'd be 7 plus negative 3, or 7 minus 3. So you turn the second one around, that's the inverse. So if this is 1 minus 2, then the resultant would be from the original tail to the new tip. That would be 1 minus 2. So here's our VF, here's minus VI, it's just flipped in the other direction, and the acceleration is delta V, or from here to here. Okay, acceleration is delta V over t, but since the time in all these intervals are the same, the acceleration vector is equal to the difference in the velocity vectors. Okay, this is a positive acceleration. Notice if you have a positive acceleration and you have a positive velocity, remember to the right's positive. If the velocity is positive and the acceleration is positive, then it's speeding up. In this motion diagram, the dots are getting closer together, and that tells us it's slowing down, right? Okay, the velocity is positive. It's slowing down. Let's look at how the vector subtraction happens here. His VF minus VI, but VI is bigger, right? If this is an initial velocity, and one of these would be our final velocity, the initial is bigger. So if we subtract it, here's where our final velocity started, and if we flip our initial velocity vector around, then it sticks out on this side further than the final velocity vector did. And so the acceleration is still the difference in those. The acceleration is this bit right here, from the initial tail to the new tip. So now your acceleration vector points negatively. So what happens if we have a positive velocity and a negative acceleration? Well, it slows down. When we had a positive velocity and a positive acceleration, it sped up. We'll say speeds up. Okay. Same direction, it gets faster. Opposite directions, it slows down. Then this motion diagram, the third one, the object's moving to the left. So this one has a negative velocity, and it's speeding up. Dots are getting farther apart. Well, look at the subtraction that they do. It's going to be VF minus VI. Well, VF is negative minus VI. That means VI turns positive, and delta V again extends in this direction. So it sped up, dots got farther and farther apart because the velocity and the acceleration were both negative. And I guess you could guess this one. It's got a negative velocity, it's heading in the negative direction, and it's slowing down, the dots are getting closer together, and sure enough, that would be a negative velocity with a positive acceleration. So the moral of this story is, you don't speed up when you have a positive acceleration necessarily. You don't slow down when you have a negative acceleration necessarily. You speed up when the velocity and the acceleration are in the same direction, both positive or both negative. And you slow down when the velocity and the acceleration are in opposite directions. Positive velocity, negative acceleration, negative velocity, positive acceleration. Instantaneous and average acceleration. In words, well, it's pretty obvious. Average acceleration is how much your velocity changes over the time interval that it changes in. Remember, our average velocity was equal to how much our position changed divided by how much time it changed in. So it's the same deal, just with acceleration now. So this is over some period of time, there has been some change. That change might have been constant, or it might have changed a lot and then a little bit, but over that period of time, you have an average acceleration. So it's an acceleration over some time interval. An instantaneous acceleration, well, it'd be the acceleration at an instant, or at a particular time, during a tiny, tiny little slice of time. This is over some larger time interval, and this would be at that second, in that instant, how fast the acceleration is changing. It might be easier to look at it on a graph. These are two velocity time graphs. In this period of time, you have a constant acceleration. So if I divided this change in velocity by this change in time, I would get not only the average acceleration over that time period, I'd get the constant acceleration because the acceleration is not changing. When in a velocity time graph, when it gets flat, that doesn't mean it's not moving. It means it's not speeding up or slowing down. The velocity is staying at this value, so it's still moving. It's just moving without speeding or slowing. And now the velocity is going from some high value down to some low value, and we could find the average velocity again by dividing the change in velocity by the time. So these are over large time intervals. But if I look at a graph like this where the velocity is changing, um, and the way it's changing is also changing. So here the velocity is changing, but it's changing constantly. It's getting bigger and bigger and bigger by the same amount. But if we look at this, the velocity is getting bigger, so it's speeding up a lot because it's really steep. The slope's really steep, right? And remember, slope equals average acceleration. So it's going faster and faster and faster. But look what happens in here. It's still getting faster because the velocity is increasing, but it's not increasing as fast. The slope is not as steep, and the slope is less steep, and the slope is less steep, and the slope is less steep. And what's happening right here? Well, for just a little bit, the velocity is kind of staying constant, and then the velocity is falling off and getting lower and lower. So in a velocity time graph where you have nice straight lines, the instantaneous velocity and the average, instantaneous acceleration and average acceleration are the same. But if I look right here, it's obvious that the slope of the line right there is very different than the slope of the line right here. And the acceleration right there would be an instantaneous acceleration, and the acceleration right there would be an instantaneous acceleration. I could find the average acceleration for the whole time interval by dividing that change in velocity by that change in time. So I could still find an average, but the instantaneous would be the acceleration right at an instant, at a tiny little piece of your graph. There is vocabulary in Chapter 3, but not a whole lot. We've already talked about velocity time graphs. We've defined acceleration. We've talked about average and instantaneous acceleration. Free fall and acceleration due to gravity, I'm not going to define for you right now. They'll come up in, I think, part 3 of this video. If you are told that you have a quiz or that you're going to be responsible for all of the vocabulary, you might want to look those up on your own.